Okay, so we're going to shift gears a little bit for the next two lectures. I'm going to be talking about a categorical view of type refinement, or type refinement systems through the perspective of category theory. And I just wanted to say a little bit in the beginning, just by way of motivation for what's the point of this. And there's something a little bit strange in programming languages research and type theory. There's sort of a mismatch between, on the one hand, a lot of the stuff we do is very formal, a very high level of rigor. So, we're used to proving theorems through the lens of the Curry-Howard correspondence, in simply type lambda calculus, or in Coq, we have very complicated proofs, completely rigorous. And we also have the meta theory of these systems that we're studying. Everything is formalized. The last couple of decades we've managed to do that. So there's a high level of rigor. On the other hand, type theory is a bit strange from the point of view of being a theory. Like if you compare it to something like group theory or graph theory, it's a bit different, and that it doesn't have the same pattern of the kind of sociological pattern you see in mathematics, where you have a few definitions which are widely accepted. Maybe they change a little bit over time, but you have some definitions and you have some theorems, people prove theorems, and there's open problems. You have examples, you have counterexamples, and in type theory doesn't really follow that same pattern so much. So you see more. We have different formal systems. People manage to prove very sophisticated theorems about those, and the proofs of these theorems. You have one system. You prove something like strong normalization. You can adapt that to another system, but it's not really, there's kind of a lack of abstraction of proving general theorems about type systems that then you can reuse those theorems directly. And maybe that's because, like I said in the first lecture, that we don't really know what a type system is. We don't really know what type programming languages are. And so, okay, this is not necessarily such a problem. There's not always, it's not necessarily a disadvantage all the time, but it's a bit different from other areas of mathematics, and it makes it a bit difficult to communicate with other areas. So, okay, so now category theory, to some extent, it addresses these issues, and people have applied category theory to type theory, to programming languages. And I think that Ed Morehouse talked a bit about this, and about the idea of category theory giving a behavioral description of systems rather than a structural description. And so this has been successful. There's the general idea that different type programming language, different type languages or type theories correspond to different categories with structure. But it's not been complete success. There's been many successes, but it's not something that everyone uses in type theory or in programming languages research. And okay, so why doesn't everyone use category theory? Part of the reason is there's many things that we care about, which aren't captured, haven't been explained for the moment, in the categorical way of looking at type theory. So, so that said, what I want to describe you is a way of, an approach to accounting for the extrinsic view of typing, and or like my belief is, part of the problem is that category theory doesn't really have, or there hasn't been a really good account for the extrinsic view of typing. And so I'm going to describe an approach which is based on viewing type refinement systems as functors. And this is something that I've been doing in collaboration with Paul-André Méliès for a few years. And okay, so I'll be talking about that. And now, before talking about that, I just want to explain what is the issue with viewing type refinement systems as categories. So, what is, why type refinement systems are, not just categories. So there's a standard way of relating typed languages, type theories, and categories. And so an example of that is simply typed lambda calculus, where the basic analogy, the basic idea is we have, so this is, I'm sure that Ed talked about this earlier, we have a term t of type B with a free variable of type A. That corresponds to a morphism from A to B in some category. And you can extend this to terms with any number of free variables by having products, a category of products, or a multi-category, okay, so you can extend this, but this is the basic picture. That's enough to describe a problem already. And so, you have this view, but now if you think back about what we've talked the last couple of days, and you look at rules like the subsumption rule. So if T has type R, and R is a subtype of S, then T has type S. So the subsumption rule. Then we looked at the intersections, and particularly the intersection introduction rule. Okay, so the question, how do you understand these rules from this perspective? And you can't really, or it's hard to make sense of it directly, because really the issue here is we have in both of these rules you have one term, which is T, being used in multiple typing judgments. Right? So here we say T has type R1, it has type R2, has the intersection type. Here we say T has type R, T has type S. But so like if we take these two premises and if we try to translate them like that F is a morphism from A to B1 and F is a morphism from A to B2. This doesn't really mean what we want it to. So in a category, so remember in a category we have a collection of arrows and a collection of objects, and each arrow has a source and a target. So here we're saying that, okay, the source of F is A, and its target is B1, and now we're saying that its target is B2, but it has just a single target. These are functions. So then, B1 really, so B1 has to be the same object as B2. So the problem is that a morphism is intrinsically associated with a pair of types. It's source, the source object, and the target object. Those are intrinsically associated with the morphism. So this view of this way of relating type theory to categories is kind of inherently biased towards the intrinsic view of typing rather than the extrinsic view of typing. So the basic idea that I'm going to be talking about, like the solution to this problem, is that we're going to build it into the model. So rather than viewing a type system as a category, we're going to view it as a functor from some category of derivations to category of terms. And the intuition here is that this is a category where the objects are types, but they're types a la Church in this intrinsic view, and the morphisms are terms. And then this category has the objects of that category are types a la Curry, and the morphisms are typing derivations. And then this functor is the kind of the erasure functor from typing derivations to terms, or the functor which forgets the refinement information. So I just want to recall the definition just of a functor, just to have reference for reference. So a functor, it maps the objects of D to the objects of E, and it maps the arrows of D to the arrows of E, and it satisfies that if you have alpha morphism from R to S in D, then f of alpha is a morphism from f of R to f of S. And the two functorial axioms, so the identity on R is mapped to the identity on f of R, and if you compose alpha with beta and apply f to it, then it's the same as applying f and composing. Okay. So I'm just recalling, you've seen this before, but I just wanted to have it. So, okay. So this is the intuition of the way that we're going to look at type refinement systems. We're going to look at them through the erasure functor from more refined types to less refined types, and from typing derivations to terms. And it's going to be convenient to, so it's going to be convenient to actually take this as a definition. So, I'm going to, for the rest of today and tomorrow probably, I'm going to say, just define a type refinement system is just a functor. Sometimes I'll call it just a refinement system. I'm used to calling it that. But so we're going to take this definition. It looks a bit, a bit silly or a bit simple. But there, so I want to begin by explaining how there is a legitimate sense in which any functor can be seen as a kind of abstract type refinement system. So this is going to be about reading functors as type refinement systems. So suppose we have a functor like this, and the intuition is these are, D is a category of derivations, T is a category of terms, and I'm going to define, so the refinement relationship. So an object R in D is, we're going to say that it refines an object. It refines an object in T, an object A in T, just, well, and we were going to write this as before. We're going to write this like that, the same notation. Just if you apply the functor to it, here I'm calling it R. Okay, so we're just going to take this as our definition of type refinement, that R is mapped to A by the functor. That's what we're going to take as our formal definition of refinement. Then we're going to talk about typing judgments. So maybe I should start drawing a little picture here. So we're going to have these two categories. Okay, and so here, okay, so we have some, I'm just drawing a little category. And another little category. Okay. So this category has three objects, A, B, and C, and it has three morphisms, F, G, and H. And then you also, this is a graph, and then we're going to view this as the category freely generated by this graph. So there's also identity morphisms and the compositions. You can compose F and G, that's a morphism from A to C. You can compose F and H. Then this is the category with four objects, and I'll just give these names. Okay, so so now suppose that we have a functor from R to T. So it's going to have to map objects to objects and morphisms to morphisms. So we're going to say, let's just say that this R1 is mapped to A, and R2 is mapped to A, and S is mapped to B, and T is mapped to C. Okay, so I just picked a random category, but this definition is just saying our convention that here R1 and R2, they both refine A, and S refines B, and T refines C. Okay? So now we just defined refinement, but now we're going to talk about a typing judgment. It's going to be a triple of a morphism in the category below. So some morphism F from A to B in T. And then some object R which refines A, and an object S which refines B. And again, this means that you have that R is in D, and it's mapped by the functor to A, and S is mapped by the functor to B. So we're going to call just a triple of these three things. So, F or RFS is a typing judgment. And I'm going to write that like this. So an arrow from R to S with F below. So here's an example. So SGT is a typing judgment. So we have morphism G here going to object speed C. We have S, which is a refinement of B, which is S is mapped by the functor to B, T is mapped by the functor to C. So we have a morphism and we have refinements of its domain and codomain. That's a typing judgment. And then this is also a typing judgment. So here we have H, it has the same domain and codomain. S refines the domain. C refines the codomain. These are all judgments. So R1, Fs, these are judgments. And we're also going to talk about subtyping as a special case of typing. Okay, so when F is an identity morphism, so in this special case, we're going to call it subtyping. Okay, so here R1 and R2, we can form this judgment where here you have, they're both mapped to A, and we can put the identity here. Okay, so let me finish the definition and then give you the example. So we talk about refinement. When one type refines another, we talk about typing judgments and subtyping judgments. But you can form typing judgments which might not be true, which might not have a derivation. So what is the derivation of a typing judgment? So a derivation of a typing judgment RFS is just going to be a morphism alpha from R to S in D, which is mapped by the functor to F. So such that R of alpha is F. So here, let's say that the functor, I defined it on objects, but now we also have to define it on morphisms. So we'll say that gamma is mapped down to the identity on A. And alpha 1 and alpha 2 are both mapped onto F, and that beta is mapped onto G. Okay? Okay. So this is our type refinement system. So that took a little while to set up. But so what can we say in this little about this little functor. So we have, I'll write it like this now. So we have gamma is a derivation of a subtyping judgment, that R1 is a subtype of R2. And alpha 1 is a derivation that F has type R1 arrow S. But now alpha 2 is a derivation for the same F that it takes R2 to S. And then beta is a derivation for that S has type G T. Okay? So for now, this is pretty abstract, but what do you see here? So we're viewing terms as morphisms in the category below. They each have types. They have unique types, so they have a domain and codomain. But now we're giving them additional typings. You can think of it. Here we've given F two additional typings, two refinement typings. We've given it the type R1 arrow S and R2 arrow S. We have two different typing derivations of that. And then there's, we have a subtyping derivation. We're defining subtyping as typing of the identity. And so you might, remember we talked about that before, about how you could reduce subtyping to typing of 8 expansion. And so we're taking that here and we're kind of translating that categorically by defining subtyping as just you have a derivation, you have a morphism above, gamma, which is mapped onto an identity morphism. Okay. So, yes. Yeah.
I have two questions. The first one is, what's the interpretation of H in the category T? Does something not anything? The functor?
So we don't have any typings we can give to it. Okay. Yeah. So we can't, so we can form this judgment. We can ask, does H have type S arrow T? But the answer is no, because there's no typing derivation for that. In the same way, we can ask, is R2, so question mark, is R2 a subtype of R1? And the answer is no, because we don't have any morphism going from R2 to R1, which is mapped to the identity.
Okay. Another question I have is, why is it sensible to map subtyping to the identity, yet say you can derive a term of type G with R2, but maybe not necessarily with R1? Does that make sense?
Are you looking at this example?
So say R2 defines R1.
Yeah.
Okay. And say with R.
Oh, so R2 here, R2 and R1 and R2 refine A.
Oh, okay. The R2 is a subtype of R1.
R2 is well. So in this case, R1 was a subtype of R2.
Okay.
Yeah. Yeah.
So
I mean, so this could be this could be odd, and this is non-zero, positive, and odd is a subtype of positive. So there's a morphism from odd to positive, and they both get mapped down to NAT. Yeah. Maybe I should. Okay. I mean, I was going to give you some examples later on, more abstract. Maybe I'll give just a little more concrete example. That would help. So. Or maybe I'll replace these by different names. So this is going to be NAT, and this is, say, bool, and this is, I don't know, string. And, well, okay, so let me give you some, is even? Okay, maybe I'll just stick with this. So, okay, here we have, just look at this side. So we have, here we have NAT and we have bool, and we have a morphism which is even, the function from NATs to bools which tells us whether something is even. Here we have odd and odd and positive, which are both refinements of NAT. So they both get mapped by the functor to NAT. And then we have false, which is a refinement of Boolean. And this judgment, so this judgment this is a typing judgment, because it's a triple of, we have a morphism here, is even, and then we have a refinement of its domain and a refinement of its codomain. And this one happens to be derivable, because we have a derivation, a morphism alpha 1 from odd to false. So we give it a derivation. Alpha 1 is mapped to is even. And then here we have gamma is a morphism from odd to pos, and it's mapped to the identity. So the odd this judgment is derivable, has a derivation gamma. Okay. So, okay, this is just it's an abstract way of defining a type refinement system. I'm going to tell you how you can talk about inference rules. This is kind of just a notation that's convenient. So I'm going to say that an inference rule is valid or admissible if given derivations of the premises, you can get a derivation of the conclusion. And here by derivation, I mean it in this formal sense. So I'll give you an example. So okay, this rule looks reasonable. It says that if F has type RRS, G has type SRT, then their composition, sequential composition, has type RRT. Now, this rule is valid for any type refinement system in this formal sense. And what does that mean? Suppose that we have a derivation alpha of the judgment on the left, and we have a derivation beta of the judgment on the right. That's just, by the definition, that means that we have that alpha is a morphism from R to S in D, and that it's mapped by the functor R of alpha is F. And then this means formally that beta is a morphism from S to T, and that it's mapped by the functor to G. Okay? And so suppose we have these things. Well, now we can compose alpha and beta. That's a morphism from R to T. And, well, R of alpha beta, when you apply the functor to it, the functoriality says that R of alpha beta is R of alpha composed R of beta, which is F composed G. So that's that's a proof that this rule is derivable for any type refinement system defined as a functor, and it's really this is really just expressing the functoriality. Now, here's another example. Suppose, as a special case of this, I have an identity term. So now you can see this as a subtyping judgment. This is the rule of subsumption. This is the subsumption rule. So if F has type R or S, and S is a subtype of T, then F has type R O T. And this rule is still valid for any functor, any type refinement system modeled as a functor, and it's just basically the same proof. The only difference is here we're taking this to be a subtyping judgment, so that means that beta is mapped to the identity. And so here we have that R of alpha beta is R of alpha composed R of beta, where this is the identity. Or this is R of beta is F composed with the identity. But then by the axiom of the axioms of categories, composing with the identity gives you back the same morphism. So we get F. So that shows that subsumption is the rule of subsumption is valid in this for any type of refinement system seen as a functor. Okay. So let's see. Okay, so the point we're taking a very abstract view of what a type system is and what typing derivations are. Typing derivations are just morphisms in one category which live over morphisms in another category. So let me give you some more concrete examples now of type refinement systems. Okay. But maybe before that. So do people have questions that we want to ask? Yes.
Are there any other interesting functors at this point here? Like, this is, I guess, kind of like a traditional functor, but I think intuitively you would think that you would have like the original category up and you would have to find the category somewhere. You would have it working. And is any of that going on?
I'm not exactly sure what you're asking. Okay, maybe I'll show you some more examples of soon. Okay, so you have a question?
Do you have an example where you have two different functions between the same category and cause up to different relationships?
Two different functors between the same categories. I don't have examples I don't have examples offhand. Maybe okay.
What about non-identity errors in the total category that map to identity errors?
Yeah, that's subtyping. So that's exactly what subtyping is. So here we have a non-identity arrow from between two objects, which is mapped onto the identity arrow.
So what if we have like anti-parallel arrows? Then do we have like isomorphism?
Then you have an isomorphism. Yeah, you have an, and so I'll talk about that. I'll talk about that a bit later. But I mean that's an important notion when you have two subtyping derivations which are inverse to each other. Okay, so maybe I'll begin just by giving you some stupid examples. And maybe that will help. Okay. So. Okay. So examples. Any category can be seen as a type refinement system in kind of a trivial sense. So here's one example. If we have a category C, there's the functor which maps every object to, one is the terminal category. It has just one object and just the identity morphism. It has no structure. So the functor which maps every object to the unique object of, so this, one is just a single object with the identity. So it maps every object to star, and it maps every morphism to the identity. So you can ask, when is this judgment derivable, or equivalently you can write this as a subtyping. When is a subtyping derivation, when is there a derivation of this subtyping judgment that A is a subtype of B, where A and B are two objects of C? Well, it's just if there is a morphism from A to B in C. So this is a trivial situation where everything is just subtyping because there's no non-trivial morphisms here. And now, yes? Yes?
So if that's the case, what prevents us from saying instead of having pause there, having even?
Yeah.
Gamma is the +1 function. How is that not going to appear in our sentence?
Right. So there, what you have, there's a morphism from nat to nat, which is successor.
It's not the identity.
And so then if you have even here, you might have a morphism from odd to even, which is going to get mapped not to the identity but to the successor function. Okay, thanks for the question. So I'll show you. Maybe I don't have time to. Okay, I'll show you quickly another silly example of a refinement system, which is just if you have a category and you have the identity functor from C to C, then you can ask, is this typing judgment, when is this typing judgment derivable? So you have, when is this derivable? Well, in fact, it's always derivable just by f. So this is a kind of, in this refinement system, every object refines itself, and every typing judgment has exactly one typing iteration, which is just the morphism itself. Okay. So now let me give you some actual more interesting examples, which will maybe give you better intuition for what's going on. So there's a nice connection, natural connection between Hoare logic and the stuff that Alex Nineski was talking about in type refinement systems. There's a natural way of viewing Hoare logic as a type refinement system in this sense. And what you do there for the category below, it's going to be one object category, and the morphisms are going to be commands. So you have different commands, C1, C2. It's a category so you can compose commands. If you compose C1 and C2, you get C1 sequential composition C2. So you just have a one object category, and the morphisms correspond to commands. And then you have another category, D, and its objects are going to be different predicates on the state. And they're all going to get mapped down to star. But now we're going to have a morphism alpha from P to Q is going to lie over some command. So let's say alpha is mapped to C1. This is just in case. So just in case, if you run the command C1, starting in a state that satisfies P, then you'll end up in a state satisfying Q. So in this refinement system, a typing judgment, when I write PCQ, it's really the same thing as writing Hoare triple, PCQ, and a derivation is a proof that the Hoare triple is valid. And okay. So let me give you another example, but a different kind of example. Okay, so this example is useful because it corresponds to some intuitive models of type refinement. Here, the category below, the category of T is the category set. So the objects are sets, and the morphisms are functions between sets. Right now, what is this category subset? The objects are going to be pairs of a set A and then R, which is a subset of A. And then the morphisms, I think that Patricia might have mentioned this example. So a morphism from the pair AR to the pair BS is going to be a function from A to B such that it maps everything in R to S. So F maps R to S. So for all A, if A is in R, then F of A is in S. Okay? So this example with the successor, so odd and you could interpret this one in this refinement system. So we have odd is really, we're going to view it as the natural numbers together with the subset of odd natural numbers. And even is the natural numbers and the subset of even natural numbers. And there is a morphism from here to here, which lives over the successor function. So, okay, I forgot to mention. So then what is this? What is the functor from subset to set? It's just the one which sends the pair of a set and a subset of that set to the underlying set. And it sends an f such that it satisfies this property to f itself. So, okay. Okay, so I can give many more examples, of course, because there's many examples of functors. But I've spoken, I've been speaking for a while, and maybe I should start to say kind of what's the point. So, it becomes more interesting when we can start to describe different type theoretic constructions as different constructions on functors. And I know that Patricia talked about fibrations and bifibrations. I'm going to talk about that now, and it's actually, at the end of the last talk, I started to talk about, I talked a little bit about data sort refinements and constructor refinements. And I also talked before about principal types, the concept of principal type. And so now I'm going to introduce a notion which is actually a kind of generalization of those two concepts. And so suppose, okay, we're working in a particular type refinement system. We have a functor, and now we have. Okay, so this is going to be a definition of the notion of push forward refinement which you can see as a kind of generalization of constructor refinements and principal types. So suppose we have a refinement R of A, and now we have a morphism from A to B. F is from A to B. So again, here when I write this, I mean R is an object in B, which is mapped to A, and then this is a morphism in T below, which has type A or B. So we're going to ask for our, we're going to push this refinement along this morphism. And so this is going to be a refinement of B, and such that, well, it has a pair of typing rules. So this judgment is derivable. So I'll name that by an inference rule. So you can this is a sort of introduction rule. So R, so F will take R to the type push FR, and then kind of elimination rule, or if we have push FR on the left, this is elimination rule. So what am I saying here in terms of this interpretation? We have our object R, and we have here a morphism F from A to B, and R lives over A. The push forward of R along F is going to be another object, push FR, and well, there's going to be a morphism from R to push FR, which lies over F, so it's mapped to F. It's a derivation of this judgment. That means that there's a morphism like this. And now what is this rule? So that's the introduction rule. What is the elimination rule saying? So suppose we have a derivation of the premise. So that's going to be, we have some way of continuing, make this a little bit bigger. We have a G, which is a way of it can compose with F. And now we have an S, which is a refinement of the codomain of G. And, well, we have a derivation of this judgment. So that there's, that F compose G has type RLS. What does that say? It says that, well, we have some derivation, I'll call it beta, where beta is mapped to F compose G. So beta lies over F compose G. That's the derivation. What we assume, this rule is saying, so assume we have that, then we can construct that. So if we have this, then we have a derivation of this judgment. And what is that going to be? It's going to be a morphism, I'll call it beta prime, from push FR to S, which lies over G. And then, okay, finally we're going to ask that there's some equations on the typing derivations that you can construct using these rules. So I'm going to write those for you. So suppose that we have a derivation beta like that. So we have a derivation like this, a beta of this judgment, and we apply the rule. To derive this. And now we compose it with this rule. We compose these. This should be the same. This should be the same, equal to our original beta. And what that is saying is that, well, precisely that this triangle here commutes. If we compose this typing derivation, so this morphism, which lies over F, with this beta prime, which we constructed by applying our transformation to beta, so this we obtained this morphism here, that should be equal to our original beta. That's what this equation is saying. And now there's another equation which says that if we have I'll call it, suppose we have some derivation eta of this judgment, so G has type push bar S, then this, we can expand this to well, we begin by applying this rule. And then we derive this by composing this with our original derivation. Okay, so we have this equation, and what that really says is that this beta prime that comes from the existence of, beta is unique. So, okay, if you remember from Patricia's talk, the definition of an op-Cartesian morphism, this is really it's a repetition of that definition of an op-Cartesian morphism in a type theoretic notation. So this is the definition of push forward refinement. And there is a dual notion of pullback, right? So, we can define pullback. And what is its signature going to be? Well, given a refinement S of B and a morphism from A to B, we can pull it back. We can pull S back along F to get a refinement of A. Then there's going to be associated with some typing rules which are just dual to these ones. And okay, so I won't give you those rules now, but maybe I'll give you examples. So just to have one example in mind, here, this refinement system has push forward and pull back, and they just correspond to the image and the inverse image. So if we have an object here in subset, and we have a function from A to B, then pushing it will just give us now a refinement of B, which is just going to be the image of R. And then pullback is the inverse image. So that's one example, but I want to tell you about another example which you might find interesting, which is if we go back to the Hoare logic example, what do the push forward and pullback correspond to there? So okay, remember in the Hoare logic refinement system, we have P's and Q's, and then we have a one object category, where is the commands. So what is push of CQ? It turns out it's just the strongest postcondition. It's exactly the same thing. The concept of push forward is exactly the same thing as the strongest postcondition, and pullback is exactly a weakest precondition. So strongest post condition, you can see that here. So if we replace this R by P and F by C, what it's going to say is that, well, so this is true. You can show that, so the strongest post condition is valid. So P, if you start in a state satisfying P, but then it's strongest. So it is a post condition, and it's strongest because for any, suppose that starting in a state P, and you run C, and then you can also run some other command D, and you get to Q, then in fact, starting from the strongest post condition and running D, you get to Q. Okay. Does that example make sense? Do people have questions here?
Question.
Yep.
Just to clarify, is it necessary to touch FR because of beta prime equals beta? Or does that not matter? Sorry.
Say again that this, yeah, that
Okay.
if you, that composing this morphism with this morphism is equal to this morphism.
Is beta prime necessarily unique?
Yeah. So that's what the two equations that I showed you, they're in the notes. I erased them, but they're in the notes. The two equations that I showed earlier, they say exactly that this commutes and that this is unique. Okay, so let me just think how much I want to get to. Okay, so okay, so these concepts of push forwards and pullbacks, they turn out to be really useful. We can talk about in different type refinement systems whether or not they have these push forward and pullback. And well, there's special names for when they have push forwards and pullbacks for all refinements for all maps. So the notion of fibration just means that you have all pullbacks pull F S for every morphism from A to B, and for every S refinement B, you have such a pullback. And so-called op fibration means that you have all push forwards, and then bifibration is that it has both. So this example, subset over set, is a bifibration, and but not every you don't always have a bifibration. You don't necessarily always have pullbacks and push forwards. Like in the example of Hoare logic, it depends. So whether you can compute weakest preconditions and strongest postconditions depends on the language of commands and the language of predicates. So maybe I'm trying to think how much I want to go through. Maybe I'll try to work through a little example just with the Hoare logic. So okay, I'll try to do this quickly. So, suppose that I'm in a little language where my commands are just, I can assign a variable to 0, I have a single variable, or I can assign it 1, or I can invert it, and I have sequential composition and skip. And then I have just very few predicates, so I can just say that x is equal to 0 or x is equal to 1. So with this example, you can work out that I can compute strongest pose conditions. So, if I start in a state satisfying P and I run C, then I'll get to some state. I can compute it in this example. It's just going to correspond to forward evaluation. If I start in a state satisfying 0 and then I run the command, and I'll get to some state which either is either 0 or 1. But then the pullbacks, or the weakest preconditions, they're not, in this little example, they're not always going to exist. And you can think about that. So if we say, okay, if we pull back x equal 1 along this operation, then it's x equals 0, because, okay, if we start in a state satisfying x equals 0, we want this command, we get to x equals 1. But if we pull back the same predicate along x equals 0, it doesn't have a weakest precondition in this language of predicates, because you could have started either in a state satisfying 0 or in a state satisfying 1. So, here the weakest precondition, or the pullback, corresponds to running the program backwards, and it's non-deterministic in this case. If you're running this program backwards, it's non-deterministic. So the weakest precondition doesn't exist. So this functor, the corresponding refinement system, is not a fibration in this case. But if we want to get back the weakest preconditions, then we have to add, represent the non-determinism by adding these junctions. Then we can compute the weakest preconditions, so we have a fibration. So let's see. So did Patricia Johan talk about the Grothendieck construction? No? Sorry? It was an exercise. Okay. So maybe I want to talk to you about that a little bit. So, I gave you a way of looking at fibrations, up fibrations, bifibrations through a type theoretic lens as these two different refinement constructors of push forward and pullback. And they have these peculiar definitions, but part of the original motivation for the definition of fibration and up fibration is that there's a correspondence between fibrations, up fibrations, and so-called index categories. So if you have a functor d over t, which is a fibration, you can see it induces a contravariant functor to cat, the category of categories and functors. And then if it's an op fibration, induces a functor, a covariant functor to cat. So a way of looking at that, I mean, I want to show you how you can derive that, or sketch it for you. So okay. Okay, so okay, I'll show you one example. So here, what I've written is a subtyping rule. Okay, like in the beginning of the lectures, I showed you a system, and I gave you some subtyping rules, some typing rules. Here I'm writing another subtyping rule, but now it has another interpretation. It has this more abstract interpretation. So what is this saying? This is saying, suppose that we have a morphism from R1 to R2, which is mapped by the functor to the identity on A. Then we're going to be able to construct a morphism from push FR to push FR1 to push FR2, a morphism alpha prime, where alpha prime is mapped to the identity on B. And well, okay, so this is how you can. This is the reading of the subtyping rule. But how do you prove it? Well, you can prove it in a purely proof theoretic style, type theoretic style. I'll just show you how to do that using the typing rules that I gave you before. Now I'm writing this for the subtyping. I'll write the identity on B here. So we're going to derive this by beginning by applying the left rule, or the elimination rule for this. By doing that, we're going to move F into the context. So, or we're going to move it into here. So we're moving from typing the identity to typing F composed with, or post-composed with the identity. That's the left rule for the push forward. Now, here I'm just going to apply a little identity, a little equation. So F composed with the identity on B is the same thing as the identity on A composed with F. And now, Right. So I'm going to go from R1 to R2. So suppose we can go from R1 to R2. That's the premise of this derivation, that we have a subtyping, that R1 is a subtype of R2. That says that we have a morphism from R1 to R2 which lies over the identity on A. And, well, we compose it now with the, here we apply the right rule for the push forward to go from R2 along F to push F R2. Okay, so this is a derivation of this subtyping rule. It's very similar in style to what I showed you before with how we can derive, we can reduce typing, we can reduce subtyping to typing of eta expansion. We're doing basically the same thing here, but it also has an interpretation in terms of functors and categories. What is this saying really? So first of all, these subtyping derivations are special. There was a question about this earlier. So and I think that this was in the course before, the notion of fiber. So if I have an object A in T, then I can talk about its fiber D sub A, which is just the subcategory of D consisting of morphisms which lie over the identity on A. So the fiber of A, you can see it as the subcategory of refinements of A. All of the refinements of A where the morphisms are subtyping derivations. And what this subtyping rule is saying, essentially, is that so if F is a morphism from A to B in T, then pushing along F gives you a functor from the fiber of A to the fiber of B. So, a functor meaning the action on objects is just the refinement rule that I showed you before. So, if R is a refinement of A, it lives in this category, then push FR is a refinement of B. It lives in this category. But then what this rule is saying is that we can transform morphisms in this category to morphisms in this category. Here we have a subtyping derivation in A, and here we have a subtyping derivation in B. So that's essentially showing that we have a functor there. But then we can also show that so every morphism defines a functor from A to B, but then this is actually a covariant. So here we have, for an op fibration, we have a covariant functor. You also want to know that when you compose morphisms in T, then you can compose the corresponding push-forward functors. And that can be expressed as saying, so if you have an object R and you push it forward along the composition of F and G, that's the same as pushing along G, so it's the same as pushing R along F and then pushing along G. And when I write equals, This really means in the sense that there's a pair of subtyping derivations which compose to the identity. So these two objects are isomorphic in this category. And likewise, if you push along the identity on A, then that's, if you push R along the identity, then that's isomorphic to R. So when you have this, that's really what this is saying, that you get a functor from T to cat. If you're familiar with Hoare logic, these rules are familiar. That's a tautology, but so okay. These are the rules for computing strongest postconditions. So if the strongest postcondition of P along C1 composed C2, here I'm writing sequential composition, is the strongest postcondition C2, strongest postcondition C1 P, and then the strongest postcondition along skip of P is just P. So these are the same equations. And then dually, there's equations for pullbacks. Pullback defines a contravariant functor. And again, you can show that this subtyping rule is derivable. So if S1 is a subtype of S2 at B, then pull F S1 is a subtype of pull F S2 at A. Again, you can derive this thing in the same style, and that's part of showing that when you have a fibration, you can get a contravariant functor from T to cat. And you can also go, so you can also go in the other direction. Given an index category, so given something like this, you can construct an op fibration. Given something like this, you can construct a fibration. That's the so-called Groton deconstruction. But what I wanted to, I think, end on is you can see the Groton deconstruction as expressing a relationship between typing and subtyping. So we talked about before about the idea that subtyping could be reduced to typing of the identity. Or through typing of 8 expansion, which is the identity. And here we see that, and I showed you how to derive these subtyping laws by using the typing rules for push forwards. So going the other way around, the Groton deconstruction says that in certain situations, when you have a fibration or op fibration, you can reduce typing to subtyping. So if you have enough push forwards or if you have pullbacks, you can reduce typing to subtyping, and that's in a bifibration. There you have both push forwards and pullbacks. So there, so I really have an equivalence there's the typing judgment, F has type R, S. That's equivalent to saying that R is a subtype of pull Fs, and that's equivalent to saying that push Fr is a subtype of S at B. Those are all equivalent in a bifibration. But I mean, kind of the philosophy of looking at functors as type refinement systems is that, well, it's nice to be able to talk about typing. It simplifies things to be looking in terms of this view rather than in this view. And one kind of argument for that here in a bifibration is, well, you can use both of these views. You can either view it in terms of the push forward or the pullback. Those correspond to two different functors, a covariant one, a contravariant one. Well, we don't have to choose when we have the whole functor, the whole type refinement system. We can talk in terms of typing and subtyping. So do people have questions about what I've talked about so far? Yes.
So in terms of like type systems that we're familiar with, the programming languages and so forth,
Yeah.
What does it correspond to if we have like just a vibration but not a bifibration, vice versa?
So, what do you mean in terms of type systems that you're familiar with?
I guess
So,
what I mean is, if I were building like a programming language with a refinement type system
yeah,
on top of it,
yeah.
what would it mean to like leave out, because these English things, you leave out the opposite English.
Yeah, okay. So I mentioned that these things, like the push forward refinements, are similar to, or you can see what I was calling constructor refinements as push forward refinements. And dually, you can see pullback refinements as destructor refinements, or destructor refinements. Constructor refinements are a special case of push forward and pullback. Maybe I'll just mention, so I was going to get to this like tomorrow, but I'll just mention it. If you define push forward and pullback, and suppose you also have intersection and union. Well, now you can express things like, well, so, okay, I'm adding two constructs. I'm going to add intersections, and I'm going to add products. So you can refine a product, A times B. If you have a refinement of A and a refinement of B, you can form a product. But so what the pullback refinements let you do is you can decompose the product as this intersection type. So, and where this, you can read this as, R is a refinement of A. We pull it back along the projection, we get a refinement of A times B. And R, if we pull it back, this should be S. If we pull S back along the second projection, we get a refinement of A times B. We take the intersection. So a pair is something which you can, if you project the first component, you get in R. If you project the second component, you get in S. And then, the dually sums, you can decompose like this. If you have,
Then
yeah.
we have the bifibration, but that's one.
Okay, I didn't hear the question.
So when we have all products and all sums in our language, then we have all pullback and all.
No, because this is actually, this is a special case of pullback and push forward where we're pulling back along, here we're pulling back along the projections from a product. Here we're pushing forward along the injections. There's another kind of special kind of pullback and push forward is, well, we can go the other way around. We can express intersection in terms of pullback of a product. So the intersection of R and S is the pullback along duplication of R times S, where duplication is the map from A to A times A. Yes?
So it seems like we can get a whole lot of stuff from pullback and push forward. So we'll start off with my confinement system being the identity function on my original
Yeah.
category type derivation.
Yeah.
And then I specify, okay, now my category of derivations, I add in pullback and push forward, right?
So you get the identity functor. So no, that's a good. Thank you for. Well, I mean that's a nice example. Exercise. What are pullback and push forward for the identity functor? If you have the identity functor, and now we have. Okay, we have something of this form. But here R, we're saying that identity of R is equal to A, so R is just A. So we have A, and we want to push A along F. What is the push forward of A along F? It's B. And
It seems like it would be, it seems to me like it would be the image of F.
I mean, formally, in this case, this is what it is. So there's probably something, another system that corresponds to what you have in mind. But in this case, because actually, there's only a single. Yeah, I mean, there's a single derivation of this map. Of this typing judgment, which is just F. So yeah, I mean, the identity functor is a bifibration. So is the terminal functor is also a bifibration because, well, there's nothing to pull back or push forward along. There's just the identity in here. Yeah.
How do I think of T cat, that functor, as typing?
So I think you can think about it as subtyping. It's for every type, we give a category which is the subtyping relation at that category. You have a collection of refinements of that. So kind of rather than defining a typing judgment, we define for each type, we define the refinements and we define a subtyping relation, and we define these push forward operations, which take us from one subcategory of refinements to another subcategory of refinements.
So with the growth and deconstruction, you had bifibration, and then you had T to cat, and you said that represented something between subtyping and typing. So is there like one corresponds to typing, one corresponds to subtyping?
I mean, the way that I view it is that when you have the functor view, so this is, you get a notion of typing. You have morphisms, you have non-trivial morphisms in here. Those are terms, and you have typing derivations for them. But then, you can look at these different subcategories A, which is just all of the morphisms alpha, which are mapped onto the identity on A. So those are subcategories, which corresponds to the subtyping relation at A. And you have a bunch of these. You have for every object you have these categories of refinements, and you have this way of going from one to the other. I mean, you have the functor, which will take you from a refinement in A to a given a morphism from A to B, you can push forward to get a refinement. If you have a refinement of A, you can get a refinement of B. So you can work in terms of subtyping. It kind of tells you that you can always work in terms of subtyping. That's also what this is saying, that any typing judgment, I can get a subtyping judgment. These are interderivable, but maybe it's more convenient. I mean, there's different reasons why it's better, in quotes, to work in terms of this rather than in terms of the subtyping. And that's what, in the last time I mentioned this thing with intersection types, that when we wanted to add intersection types, we had to add a distributivity rule to this rule that said that this is a subtype of this. We had to add this axiom which kind of mixes the arrow with the intersection. Whereas when we just talked about typing, we could we had introduction rules for function types, introduction rules, introduction and elimination rules for arrow types, and we could derive this law by 8 expansion.
So the kind of refinement systems that I work with on a daily basis, like in eco and stuff,
Yeah.
in addition to accounting for restricting numbers